Okay, let's start, can we? I apologize for the delay. The last day is always full of adventures. And our adventure for today is going to be the following. I'm going to tell you how to do measurements on your system. And in fact, by doing measurements, apply a unitary operation to it. Let me explain you what the surprise is. Suppose you have some spin 1/2, like in the state A up, plus B down. You measure as Z, with probability A squared, you get state up. With probability B squared, you get state down. You destroyed coherence of the state. You don't have a superposition anymore. What we're going to do today is something different. We're going to do some measurement, and as a result of that, a state like this will go to some unitary operation times A up plus B down. Of course, this is not going to happen just like this. I will need to define a system that allows me to do that. And I will use the system properties in a clever way, and I will use the measurements in a clever way, and will apply a unitary operation. So, to do that, I need to prepare the ground. And most of today will be preparing the ground, and maybe the very last half an hour or so will be about applying the unitary operation. So let me start preparing the ground. And what I need to introduce is a system called the Kitaev chain. This is going to be the system that will allow me to use the measurements in a clever way. And the first thing I need to remind you in order to introduce this system is second quantization. In Ukrainian, it's вторинне квантування. Raise your hands who knows that. Okay, so about 50-50. Let me briefly remind you so that we agree on the notation, and those who don't know, I'll try to tell all you need to know. So, the basis of second quantization is that, suppose I have a quantum system. I have some orbitals. Say I have hydrogen atom level n, orbital angular momentum L, angular momentum projection m, n, L, m, some multi-index that parameterizes orbitals. If I have a free particle, this can be its coordinate or even the set of 3 coordinates. Whatever are the quantum numbers that parameterize my system, I'm going to denote them alpha. It can be this, it can be that. Whatever is the complete set of quantum numbers parameterizing orbitals in my system is alpha. And then I'm going to introduce an operator, A alpha, and this is going to be an operator that annihilates an electron in state alpha. And I'm going to have its Hermitian conjugate, which is an operator that creates an electron state alpha. You'll see in a moment how it works for those who don't know. And yeah, so the most surprising thing for those who don't know the second quantization is I know how to describe many electrons. I have a wave function of coordinate of the first electron, of coordinate of the second electron. I have some wave function phi of x1, x2, xn. It's anti-symmetric. Phi of x2, x1 is minus phi of x1, x2. It's all I need to know about a state of a quantum system with n electrons. What are we talking about? What creation annihilation operators? If I want to describe a state that has n electrons and is described by a wave function phi, I can write it as follows. I can write it as the integral of this wave function with a dagger x1, a dagger x2, a dagger xn times something I will call vacuum. It's a state without any electrons. And I have this normalization factor. So if I want to describe a state that has n electrons that are described by some wave function, in the language of second quantization, this is the state. This is vacuum. It's a state without any electrons. And each of these operators, by definition, it creates an electron in some state. So let's consider some simple example. Let me take a state with 2 electrons. And the first electron sits in point A, and the second electron sits in point B. But of course, electrons are fermions, so I have to anti-synchronize this function. Then by this definition, it's going to be 1 over square root of 2 times 1 over square root of 2 from the wave function equal dx1 dx2 delta of x1 minus a delta of x2 minus b minus delta of x delta of x2 minus a times ax1 dagger, ax2 dagger times that. And the integrals are killed by the delta functions. So this is equal to 1/2 a dagger a dagger b minus a dagger b a dagger a times that. So looks very natural, what you would expect. We have a state with no electrons. You can create 1 electron in state B, then the second one in state A. Or you can create them in the opposite order, and since they are fermions, it should be antisymmetric. But the second quantization accounts for the antisymmetry as well. Basically, I know that if I have an electron in state alpha, I want to create an electron in state alpha and another one in state beta. There is anti-symmetry, so this is going to be essentially the same state, but up to a minus sign. In other words, the other hand. Good. In other words, the anti-commutator of A alpha dagger and beta dagger is equal to 0. And if I take the Hermitian conjugate of this identity, I will get that A alpha and beta also anti-commute. And then there is also an extra identity which tells me that A alpha dagger and beta anti-commute. They're related to different electrons unless they are talking about the same orbital, and then it's like this. Which totally makes sense, because if suppose I take a vacuum state and I apply this A alpha dagger, A beta plus A beta, A alpha dagger here. I have a whole array. I just need to find the good ones. Right, so this thing is 0 because I'm trying to annihilate an electron which in a state with no electrons at all. So A beta times 0 is 0. And this one, I'm creating an electron in state alpha. Then if I'm trying to annihilate an electron in state beta, which is a different state, there is no electron there, I will get 0 again. And if I'm trying to annihilate an electron, I put an electron, and then I annihilate the electron in the same state. Be this. I put an electron, I removed an electron. And this follows from this identity. So, in principle, all you need to know to work with second quantization are these three identities. And you need to know, but we won't really use that, how many electron states are represented in terms of their wave function and second quantization. Then if I come back to this example, I see that by anti-commutation of A daggers, this is simply A dagger A dagger B times vacuum. So I wanted to describe a state with two electrons where one of them is at A, the other is at B. How do I do that? I simply write I create an electron in A, I create an electron in B. That's my state. That's the convenience of second quantization. You don't need to think about anti-symmetrization. The formalism does everything for you. what happens, we need to do a couple more exercises to get the feel of the formalism, and this will help us later when we build upon this formalism. So I have this state with two electrons in positions A and B. And I want to apply an operator A, which kills an electron in that state. There's nothing simpler. I apply AA to this state. Now I start using these identities. A dagger by this identity is equal to 1 minus A dagger, A B dagger. So this gives me AB dagger 0, and this gives me minus A dagger, AB dagger 0. Now, these have different indices, so they anti-commute. So I should simply take this through, switch their places and change the sign. So this is equal to AB dagger times 0 plus A dagger, AB dagger, A times vacuum. And as we said before, if I remove an electron from vacuum, the state is annihilated. There is nothing to remove. So this is equal to 0. Totally makes sense. I had a state with two electrons. I removed one of them at position A. I get a state with one electron at position B. What will happen now if I want to remove an electron at position B? Let's go and calculate. This is almost trivial, but there is one surprise. I know that these anti-commute, so this is minus A dagger, AB. This is minus A dagger, 1 minus A dagger, B, AB, 0. AB annihilates the vacuum, so I get minus A dagger, A, 0, which makes sense. We removed the electron at position B, we are left with the electron in position A, but there is a sign. And the sign may be important, it's there, it reflects the anti-symmetry of electrons. It may be important sometimes. Finally, we'll need the following knowledge, that if we have an operator, A alpha dagger A alpha, it counts the number of electrons in state alpha. Let's check that. So I switch the order of these two using that identity, and I get this, which is 1 if alpha here is A, and 0 otherwise. And here I get some operators. So here I get delta alpha A dagger alpha, A dagger beta 0, minus A dagger alpha, A dagger A alpha, A dagger beta 0. Now I continue switching the order. Okay, so my ones don't run quite well either. I continue switching the order. Here I add delta alpha A, so I can replace this alpha with A, no problem. And in the second term, I'm switching the order. Again, I will have a delta here, and a term with A alpha on the right. So I will have A alpha dagger, A dagger, delta alpha B minus A dagger B and alpha minus that. As we know, A alpha annihilates the vacuum, so we're left with this delta. So we're left with delta alpha A dagger A B dagger minus A dagger B, A dagger A delta alpha B times vacuum. And this we can switch the order, so it's going to be delta alpha A plus delta alpha B, A dagger A B dagger times vacuum. Remember, we applied this A dagger alpha operator to the state, and we found that this state is an eigenstate of this operator. If alpha is A, it's an eigenstate with eigenvalue 1, so it tells us there is one electron at A. If alpha is B, it tells us there is one electron at B. If alpha is not A and not B but something else, both things are 0, and it's an eigenstate with eigenvalue 0, which tells us that there are no electrons in states other than alpha or B, A or B. So once more, this operator counts the number of electrons in state alpha. This was the end of the standard second quantization reminder. Now we're going to do something non-standard, or not so standard. And we're going to introduce, we're going to introduce Majorana Can you see this? Okay. Not really. Okay. So it seems not about the markers, it seems to be about the liquid, the eraser. Oh, I see. I see. So I should use this to erase everything, and I should use this to erase parts. So we're going to introduce Majorana operators. These Fermion creation and annihilation operators, since one is the Hermitian conjugate of the other, they are not Hermitian. So they are like, Hermitian is like real numbers of the operators. These operators are not Hermitian, they are not real, so they are like complex. So we can introduce the real and the imaginary part of the Hermitian and the anti-Hermitian part. So let me take an operator A alpha, and let me define gamma 1 alpha like this, and gamma 2 alpha like this. Okay, I need to check the sign of the definition, yes. These are like the real and the imaginary part of the electron operator. These operators have some nice properties. First of all, it should be easy to see that these operators are Hermitian. Second, these gamma j alpha, when squared, they equal to 1. Let's check this, for example, for this operator. Let's calculate gamma 1 alpha squared. It's A alpha plus A alpha dagger times A alpha plus A alpha dagger. We have A alpha plus A alpha dagger A alpha plus A alpha dagger plus A alpha dagger A alpha dagger. What is this? This is like 1/2 A alpha plus A alpha. This is 1/2 the anti-commutator A alpha. So if you remember the identities about the anti-commutation of A alphas, they are 0. They are 0 even for A alpha and beta. Here we have A alpha. Which kind of makes sense in this case for a different reason as well, because this A alpha squared is, I'm trying to remove 2 electrons in state alpha. But because of the Pauli principle, there cannot be more than 1. So A alpha squared is always equal to 0. For the same reason, A alpha dagger squared is equal to 0 because I cannot add more than one electron to the state. I cannot add, I cannot remove. What I'm left with is this. This is the anti-commutator of A alpha dagger. This is equal to 1. So we see that gamma 1 alpha squared is indeed equal to 1. The same can be done for gamma 2 alpha. And I can actually prove a property which is way, way more powerful. I have operators gamma j alpha. I have operators gamma k beta. A different Majorana obtained from a different fermion operator. This is going to equal to 2 delta jk delta alpha beta. So, if Majoranas belong to different fermions, they anti-commute with each other. Even if they belong to the same fermion, but these are two different Majoranas, the real and the imaginary part, they also anti-commute with each other. And if this is really the same Majorana, then gamma squared is equal to 1. So we have 2 gamma squared, which is equal to 2. These are the properties of Majoranas. Yes, these are the properties of Majoranas. We're going to need one more property. This property is about knowing what is operator I gamma 1 alpha, gamma 2 alpha. Can anyone guess what this operator will be? Okay. If we cannot guess, let's go and calculate. So it's equal to A alpha plus A alpha dagger, A alpha minus A alpha dagger. This is equal to A alpha squared is equal to 0. So this is equal to this minus this. I use the anti-commutation relation of A alpha and A alpha dagger, and I arrive at this identity. Which means that essentially this operator measures whether there is a fermion in the state alpha or whether there is none. If there is a fermion, this operator will have eigenvalue 1, and this operator will have eigenvalue 1. If there are no fermions in the state alpha, this operator has eigenvalue 0. 0 minus 1 is minus 1. This operator will have eigenvalue minus 1. So if I look at this operator, it's as good as if I look at the occupation number of the operator. Good. So this was a nice mathematical exercise. We defined these Majorana operators, but what did we achieve? We defined the real part, the imaginary part. Fine, can we use it for something? Can we put it to some good use? Can we do something we couldn't do before? We can. And the thing we can do is to combine Majorana operators from different electron operators. let me define new fermions. Let me define psi 1 equal to gamma j alpha plus gamma k beta, and psi 2, which is gamma L rho plus gamma m sigma with i's. So I follow the same pattern. If I want to define A alpha, it's like gamma 1 alpha plus I gamma 2 alpha. I follow exactly the same pattern, except I combine Majoranas belonging to different orbitals. And what I want to tell you is that these, they are as good as our original fermions. For example, you can show, yeah, there should be one option. For example, you can show that psi 1 square is the same as psi 2 square and is equal to 0. You do a simple calculation, you show that. Another thing you can show is that psi 1 psi 2 is equal to minus psi 2 psi 1. You can also show that psi j psi k dagger anti-conduce to delta jk. Yeah, most importantly for us, I gamma j alpha gamma beta is 2 psi dagger 1 psi 1 minus 1. So what we see is that with Majoranas, we split one fermion into two Majoranas. We can combine any pair of Majoranas. This becomes a new fermion. And it's as good a fermion as the original one, except for this one, if alpha is spatial coordinate, then this fermion is local. And this fermion is distributed over several orbitals. It's not local in space. Otherwise, this operator, which is the product of Majoranas, tells us whether the fermion is occupied or not. Everything is the same. Okay, so that was the exercise of introducing Majoranas. And now we will put Majoranas to real use. We'll put the Majoranas to real use because we finally get to consider the tide chain. What is the tide chain? Suppose I have n orbitals. I can put an electron here, I can put an electron here, I can put an electron here. Any electron can be in any of the n orbitals. And I have a Hamiltonian that governs my system. The Hamiltonian is going to have 3 terms. And that's not necessary, but I will assume that all the 3 coupling constants appearing in the Hamiltonian, they are real. So I have electrons that leave on this chain, and they are governed by this Hamiltonian. Let's have a look at what this Hamiltonian describes. Start with this term. This is the simplest term. It tells me that if my electron, if site J is occupied, this is J, if site J is occupied, then there is a contribution of minus mu over 2 to the energy. And if site J is empty, there is a contribution of plus mu over 2. So what this term wants to do is that if mu is greater than 0, then it wants to keep all the sides occupied. And if mu is smaller than 0, then it wants all the sides empty. So that's the simple term. If I didn't have the other terms, everything would be simple. From u greater than 0, I have all the sides occupied with electrons. From u smaller than 0, I have no electrons in the system. And from u equal to 0, any state is fine. That's not the only term. I have 2 more terms. What is this term? Can anyone guess or tell me what this term describes?
Jumps.
Jumps, yeah. So this thing, it takes an electron at site J, and it creates an electron at site J plus 1. So it wants to take an electron here and move it here. It describes the electron jumps, the electron hopping along the chain. And the other term describes hopping in the opposite direction. This is the term that tells me my electrons would like to jump around. Finally, I have this term. Can anyone guess what this term is?
Annihilation and creation.
It is. Annihilation and creation of what?
pairs of electrons.
Pairs of electrons. When do we have pairs? When do we think about pairs of electrons?
Cooper pair.
Cooper pairs, superconductivity, yes. This term describes superconductivity. There is a condensate of Cooper pairs, denoted by delta, and a Cooper pair can pop up, split into two electrons, or two electrons can form a Cooper pair and fall into the condensate of Cooper pairs. This is the superconductivity. You can notice this is not the conventional superconductivity, because the conventional superconductivity is about pairing electrons of different spins. You have an electron spin up momentum there, spin down momentum there. You create a Cooper pair out of them. There is no spin here. And also the electrons, okay, there is no spin here. So this is unconventional superconductivity. This is called P-wave superconductivity. For now, just let's go with this simple model. And maybe if we have time, I will briefly tell you how to get such a thing. So this looks quite complicated in Hamiltonian, especially that it does not conserve the number of electrons. So my states will be superpositions of different numbers of electrons. The eigenstates, possibly. Nevertheless, we can solve it. And the way to solve it is to introduce Majoranas for each of those fermions. So I will introduce let me check that all the signs are correct. Yes, seems so. And then I can write the Hamiltonian down in a very simple form. It's going to be equal to this. You can see what terms contributed where by tracking that, okay, this is mu, so that comes from the term with mu. And this is t, so this comes from the term with t. And this comes from the term with delta. So we rewrote Hamiltonian in terms of Majoranas like this. How does it help us to solve it? At least it helps us to interpret what each of the terms want. So previously we had sides J, 1, 2, 3, 4. Now for each side we have two Majoranas. this mu term is simple. This is gamma 2j minus 1. This is gamma 2j. And this mu term, it has this operator I gamma gamma, which has eigenvalues plus or minus 1. So it wants, depending on the sign of mu, either the eigenvalue plus or the eigenvalue minus. So it wants the site either occupied or empty. Just the same as we saw it there. What does this term want? Have here t plus delta and the gamma gamma operator. So this term wants a specific eigenvalue of this gamma gamma operator. What is this gamma gamma operator? This gamma gamma operator is this operator. So it tells us, make me a fermion out of these two Majoranas, and I want this fermion, say, occupied. This is what this term tells us. Finally, there is this term, which tells that make me a fermion out of these two Majoranas, and I want them occupied. Obviously, we cannot satisfy all the requirements because we're going to have also the other term that wants this side occupied. So the black terms, the mu terms, want this side occupied, these guys want this occupied, and they are in conflict. So there is going to be competition between these terms. Let's consider some simple cases. Let's take, for example, t equals 0, delta equals 0, mu, say, less than 0. So I want it less than 0. Yes. Then my Hamiltonian is simply absolute value of mu over 2, sum over j, I, gamma to j minus 1, gamma to j, and the Hamiltonian tells me I want the eigenvalue minus 1. I want all of the sides empty. I want no electrons in my system, all of the sides empty. And I have another simple case. Mu is equal to 0, and t is equal to delta, and all are greater than 0. Then what is my Hamiltonian? My Hamiltonian is t sum over j, I, gamma to j plus 1. So this means that, okay, I have my sides. And each of the terms tells me tells me I want to take this pair of Majoranas and I want eigenvalue -1. Which means I want to form a fermion out of these two Majoranas and I want it to be empty. It does that sums for a bit more and asks that for this pair of Majoranas as well. Now notice one thing, is that I have the first Majorana left, I have no one to pair it with, it does not appear on the Hamiltonian. And I have the last Majorana left, I don't have anyone to pair it with. So I have gamma 1 and gamma 2n, they do not appear on the Hamiltonian. They commute with the Hamiltonian. So I can form a fermion out of them. And this fermion operator is going to commute with the Hamiltonian. And therefore, the Hamiltonian does not care whether this fermion is occupied or empty. So in this limit, the ground state of my chain is twofold degenerate. And the two ground states, they correspond to whether this, I would like to have a different color, but I don't have one. So they correspond to this non-local fermion being either occupied or empty. And how can I change the state whether this fermion is occupied or empty? Say, if I apply A1, it can act on this Majorana, it can put the electron in this pair, but this costs a lot of energy, so most of the time it wouldn't like to do it. It will be suppressed by the energy cost. So what it will do, it will actually put the electron here. So A1, which is gamma 1 plus I gamma 2. The action of gamma 2 costs energy. So A1 in this ground state subspace acts as gamma 1. It switches the occupation of this non-local fermion. Also AN, it acts as gamma 2n. So I can put an electron here. I could have my non-local fermion empty. I can put an electron here. And then I can take an electron here. And my system is back to the original state. Sounds weird. That's how it is. And that's the solution. The next chapter is called Typological Protection. So we obtained this solution. Looks nice, looks beautiful, looks counterintuitive. That's all what we like about physics. But you know, I have to fine-tune my parameters to get this solution. I need to put the chemical potential to zero, I need to put the tunneling rate, the hopping amplitude and the superconducting pairing amplitude to be equal. I won't be able to do that realistically exactly. And if I want, then I will have deviations from this nice and beautiful limit. And what will those deviations do to me? Will they destroy the degeneracy of my Fermi? Will they bring any energy to it? What will these deviations be? There will be some gamma-gamma terms, either acting on one side or on neighboring sides or on neighboring sides like that. There will be some local perturbations to my Hamiltonian. And in the bulk, they are not going to do much. If this is large, the gap, the energy cost to do some perturbation in the bulk is large, these perturbations won't affect the system much. Can they give energy to this fermion? Can they split the degeneracy? Well, to split the degeneracy, the perturbation has to act on gamma 1 and gamma 2 amplitudes. What can be the degeneracy splitting Hamiltonian? It can be something like epsilon psi dagger psi. Tells me that if my fermion is occupied, it has energy epsilon, and if it's empty, it has energy 0. Or rather, I'd rather write it like this, in a symmetric way. That if it's occupied, it has energy plus epsilon, and if it's empty, it has energy minus epsilon. But you know, I know what this operator is. It's I gamma 1 gamma 2n. So to have something like this, I need a perturbation that acts on both ends of my chain. It has to be a very, very non-local perturbation. I don't have those in my original Hamiltonian, and realistically, I won't have perturbations like that in any Hamiltonian. This is not local. I take a long chain, and any interaction has some reasonable finite range. So we conclude that this is not possible. We are always going to keep the degeneracy. That's if we assume that the bulk gap is large, infinitely large. This hopping amplitude, the superconducting pairing is infinitely large. This is an exact statement. If the statement, as in any realistic system, these amplitudes are finite, maybe large compared to our perturbations, we're close to this limit, but t is not exactly delta, there is some deviation, delta, say t minus capital delta, I will call it delta. Then what can I have? I can have a term in my Hamiltonian that couples this and this. Then I can have a term in my Hamiltonian that couples this and that. And I can expand those terms in perturbation theory. As you know, if I have this term, okay, it comes with delta amplitude, but it creates an excited state of energy T. Then the next perturbation order comes again with delta over T. So this epsilon is going to be delta over t to power n. So if my deviation delta is smaller than t, and I take a very long chain, n goes to infinity, this epsilon goes to 0. In other words, this epsilon is exponentially small in the chain length. Which means that since I need a non-local perturbation to get this degeneracy splitting, I can only construct it from local perturbations by applying many local perturbations, and that has energy cost, and the more local perturbations I have to apply, the less likely it is. So the smaller will be the degeneracy splitting. This property is called topological protection.
But this is only for H Majoras. Because in the bulk there is very low this power and large. I mean, if you consider perturbation for all Majoras,
yes,
then it seems
if I consider an operator
to the power of n.
Yeah, once more, if I consider an operator that involves all Majoranas, say the product of gamma 1 to gamma 2n, absolutely, if I add that to my Hamiltonian, it gives me exactly this term. The problem, however, is the product of all Majoranas is a very non-local operator. It's like the density on site 1 times the density on site 2 times the density on site 3 and so on. It's very unlikely to get such an operator. I could think of, say, a Coulomb interaction, the density on the first side, the density on the last side, and some Coulomb potential between them. Okay, this will give me something like this. Still, Coulomb potential decays as I increase the length of the chain. It may not decay exponentially, it decays power law, but still it decays. So, once more, either my perturbation has to be non-local, which is unrealistic, or my perturbation effect is exponentially suppressed. And this is called topological protection. And there is a reason it's called topological protection. And the reason is topology is a branch of mathematics that studies properties of geometrical objects up to deformations. Say, I have two rings. One is inside the other. There is no way I can move them, I can deform them. There is no way for me to take one ring out of the other. Basically, there are two ways. Either I should apply something really non-local, I should invent an extra dimension and move all of this ring outside of that. Then I can make them disjoint. Or I can break one of the rings, and then, you know, it's simple. Same here. I have to either apply a non-local perturbation, as Gleb suggested, to split the degeneracy, or I need to apply a really big perturbation that, if delta is larger than t, if my deviation from the desired parameters is larger than the system gap, then yes, this no longer falls down as n goes to 0, it actually grows. So I have to either apply something non-local, or I have to apply something that big that the system breaks, just as with the rings. This property is called topological protection of the degeneracy.
Is it important that here that the amplitude doesn't depend on the side number?
It's not that important. If it depends on the side number, I will have a product over all sides delta over t. But the most important part, if I have a product of many numbers smaller than unity, I'm going to get something small. It may be complicated to solve, but you expect that ultimately the protection is there independently of whether the system is translationally invariant or not.
May I ask, why is the exponential minus?
Plus. Plus. But this is negative. Thanks for spotting. Thanks a lot. I have a few minutes before the end of this lecture to tell you about some real implementations of this Kitaev chain, because as I told you, the superconductivity, the chemical potential that prefers some density is finite. Everyone knows. The electron jumping, the electrons move around the system, that's not difficult to organize. The superconductivity is a strange sort of superconductivity. So you may wonder whether it's possible to make such a system in reality. Turns out it's possible. I'll briefly tell you how. What people these days do when they want to get Majoranas, they do the following. They take a conventional superconductor and they put a nanowire on top of that. And the Hamiltonian of this nanowire is this. By electron operators here, I mean a column of of electron operators. One would spin up, and one would spin down. And let's have a look at what the Hamiltonian has here. What is this? This is essentially p squared over 2m. This is the thing that makes the electrons move to the left and to the right. What is this? This is the chemical potential. It was denoted by the same mu. What is this? This is superconductivity. This is conventional superconductivity. You see, I have electron spin up paired with electron spin down. So I take any superconductor, I have that sort of superconductivity. No problem at all. There are two extra interesting terms. This one is simple to understand. You see, it's spin-ups have more energy, spin-downs have less energy, so it's the magnetic field. Simply the magnetic field. This is the most interesting term, and this is what allows everything to work. This is spin-orbit coupling. You see, it's essentially coupling between the spin direction and the momentum. A particle with sigma y up has a term which is positive in momentum, sigma y down, a term which is negative in momentum. So we can draw the energy of this Hamiltonian. I remind you, I dropped the last two lines for now. The first term is p squared over 2m. Don't draw it with me, you'll draw the picture at the end. Then I have minus mu, so I take this parabola down. Now I have this terms. Say I have p squared over 2m plus p. What does it mean? It's like p plus something squared and some energy shift. So it's like spin up y is going to be here. Spin down y is going to be here. This is again down y, this is up y.
So which one is higher? Which one is higher?
Pardon?
Higher. Which one is higher?
They are the same height because you see it's p squared over 2m plus minus alpha p, so it's p plus m alpha plus minus m alpha squared over 2m minus m alpha squared 2, something like that. You see they are the same height, they are simply shifted in the momentum space. So this is spin y. Now I have the magnetic field term. The magnetic field term couples to sigma z, which is not sigma y. Sigma z would like to flip up a y into down a y and vice versa. But it's translationally invariant. It cannot give me any momentum shift. Only when the two momenta inside it can flip one into the other, and then it opens a gap. Because if you had a matrix they were degenerate, so we have some energy, nothing. And now I get this H that wants to flip them. Then the two eigenenergies of this will be plus minus the energy they had previously plus minus H. So instead of two degenerate states, I'm going to have one with energy just above and the other with energy just below. So I'm going to have this gap opening here. Like this. And you see something funny happens now. I have like two bends. Bend number one, where here the left movers, the electrons with momentum to the left, have spin down in y direction. The electrons with momentum to the right have spin up in y direction. And as momentum changes, the spin changes, and the opposite happens on the other hand. And you see all of that happens because we have the two parabolas, the two spins shifted. So that's the reason why this term is called spin-orbit coupling. It couples the spin to orbital motion. But for us, what's important now is that we have, if we tune chemical potential to be somewhere in this region, the only term we have unaccounted for is superconductivity. And you see, we had conventional superconductivity because of the conventional superconductor that proximitize our nanowire. But now, I don't have, I have spin up right movers and spin down left movers. So I take that part of superconductivity. But my conventional superconductor also would like to pair spin down right movers to spin up right movers, but at these energies I don't have any. I'd like to have A, P up, A minus P down, and AP down, A minus P up. But you see, I only have AP up, A minus P down, and not this part. So I kill half of my conventional superconductivity. And it turns out that it brings you the P-wave superconductivity. And therefore, if you do everything correctly, if you tune the magnetic field in this gap, what you get is two Majoranas at the ends of the nanowire. And perhaps be proud how close we came to modern days, because this was proposed back in 2010, so 9 years ago. The first confirmations came in 2012, 2013, that yes, there are Majoranas. Then people started doubting, and until now, people build variations of this device to convince themselves that there are Majoranas. And some people are starting to go and try and use Majoranas for qubits, because what's good about these Majoranas? Have two states, have two degenerate states, no energy between them. That's a qubit. Now you can try and do something with it. But about that we'll talk in the second lecture, after the break.